Well, hi everyone, and welcome to this month's SLCan webinar presentation. Today's presentation is on bringing sustainability to the students, a mechanically focused post-secondary case study. Today's presenter is Kevin Shea. Just a brief bio on him. After graduating from McGill University's Faculty of Mechanical Engineering in 2006, Kevin began his professional engineering career in Calgary, where he worked for 6 years. In 2014, after making a move to Vancouver, he joined the AME Consulting Group and is now a partner in the firm. He's passionate about energy efficiency and sustainability. Kevin is a certified passive house designer and a lead green associate who takes a personal interest in leading edge technologies and innovations that enhance sustainability in mechanical design. Kevin is leading the newly formed technology and science team at AME, focusing on delivering high performance design with cost-effective solutions. It gives me great pleasure to welcome Kevin, and with that, I'll turn it over to you, Kevin. And I would just ask that if anyone has any questions throughout the presentation, that you key them in on the information bar that should be on your screen, and we will get to them upon the completion of Kevin's presentation. And with that, it's all yours, Kevin.
Awesome. Thanks a lot, and hopefully I don't go too fast or too slow on this. It's a little bit weird presenting to empty void space, but I'll do what I can, and hopefully we'll get through everything in the right amount of time. So just to get going, there we go. So objectives for today is looking at the design challenges and strategies, for the project that we had, which is down in Surrey, here in the Lower Mainland near Vancouver. Sustainable engineering strategies that we used for the lab, student interaction and learning lab component. That's obviously going to be kind of coming into play as the students get into the lab. And project delivery method, which was a little bit different on this project. So this was still kind of the better photo that we had of the project, where it's pretty well done, but it shows the high-rise building that we're designing next to, which kind of comes into one of the design challenges that we had moving forward. So we'll get into that, but just a snapshot of what it looks like. We're the little building on the left of the high-rise there. And some building metrics for everybody. We've got about 155,000 square foot of occupiable area with one level of parkade underneath of that. And there's a full parkade to basically the property line. 5 stories at about 5 meters each with mechanical penthouse on top of that. And then it'll facilitate about 320 undergrad students and 100 graduate students and researchers. So basically floors 1 and 2 are for undergrad students and program, and then from about 3 to 5 are for research components for the university. And so I just wanted to show a little bit here. The red on the top of the page in those 2 floors are the lab components, the wet lab components. The green kind of teal color is the admin student classroom area, and then the yellow is the big atrium that kind of runs up the building. And so on the lower floor, the lower 2 floors, it kind of wraps around a little bit where that big tiered auditorium is, and from 3 up, it's just open to below there. So just to give a bit of a reference. So our first challenge that we had was building next to a high-rise building, and in the future there could be another high-rise that SFU actually builds next to us. And so the first stage of trying to figure out how to exhaust lab air out of a building and not affect our neighbors too much was to engage wind study experts and do an exhaust dispersion study. And so we engaged with gradient wind engineering, and the big issue that we had was trying to get all of the anticipated chemicals. From there, looking at the typical high plume exhaust as compared to another strategy. And so the solution that we had for this was two-stage exhaust out of the building, with stage one being variable flow from the building that's reacting to our labs and the VAV boxes in those labs. So maintaining pressure in the building and exhausting up into our constant volume system, which is up on the roof of the penthouse. And the big thing that we saw when we did our wind study was, based on kind of what's on this on the photo, you see the lab exhaust there, and we looked at high plume exhaust, and the high plume exhaust basically just took all that dirty lab air and wrapped it around with a bunch of clean air on the outside of that lab exhaust air, and it basically went up about 20 stories and just hit the building with all of those chemicals still kind of in a big plume of air. So it was probably the worst way we could exhaust out of this building. And what we found was actually having a lot slower moving air allowed it to disperse quicker and to the levels that we needed before it hit that high-rise building. And so the units up on the roof are constant volume for the reason of mixing outside air with that lab exhaust air. And so we've got typically out of the labs about 50,000 CFM, and those rooftop units are at about 90,000 CFM. So they're mixing clean air and diluting air prior to exhausting it out of their stacks at about 3,000 feet per minute. And so it was a lot of iterations trying to figure out exactly what the best solution for this was. The next strategy, or the next issue that we saw was the 5-story atrium and the thermal comfort issues that we knew we were going to have. We're not as cold here or as hot in the lower mainland, but we still have the fact that this big atrium, and you can see the glazing on kind of the bottom left and the center of the building there, that's all facing east. And so we knew that we'd have big solar gains, and we knew that we would have some issues in the winter with a lot of the chill coming down the windows. And so we wanted to make sure we modeled this to avoid anything, any discomfort with the students, because that atrium was going to be used for gathering spaces for not just the university, but possibly rented out to other people for different events. And so thermal stratification, draft effects, and solar gains were what we were looking at. And so our thermal comfort model actually helped us design our fan coils around that atrium in terms of how much ventilation we needed with the supply air temperature that we had. And you can see at the bottom of this page the different ranges that we had in terms of CFM per square foot and out of those fan coils. And in the end, we kind of had a bit of a mixture where on levels 2 and 3, we had about 1 CFM a square foot. And as we went up the building, we needed more cooling because of that stratification that was happening in that big atrium. Up to where the level 4 and 5, we're at about 2 CFM a square foot for the design of the fan coils that are feeding the corridors that are on the outside of that open atrium space, just to maintain comfort for those students that are going to be sitting around those areas in the corridors. So it was interesting that kind of drove that design. And along with that, in terms of the thermal comfort analysis that we did, part of the solution was in-floor heating and cooling on that main floor area with displacement ventilation. And as per the charts here, increased cooling and heating to the fan coils around the perimeter as well. So those fan coils are only on levels 2 and up. So the main floor is cooled strictly with the in-floor and displacement ventilation. And so that was interesting that our thermal comfort model helped drive the design of that area. The next challenge that we had was district energy. And in the Lower Mainland, district energy is a pretty big thing that started about 15 years ago. And the city of Surrey has got a district energy connection requirement in the area that we're at. And what that means is, unfortunately, they mandate requirements around heat recovery, and they mandated that we couldn't have active heat recovery in our exhaust air stream. And so it also limited how many lead energy points we could get at 10, because the district system was pretty new, and so they didn't have any metrics on how efficient their system was. So that limited what we were going to do, or what we might look at in terms of using an active chilled coil on the exhaust air stream. And so looking at two options, one was utilizing a small heat recovery chiller for just the simultaneous heating and cooling loads, and the other was utilizing a water side economizer on the chilled water side. And so as you can see on the chart there, when we look at the bottom two, the low processed water leaving temperature and the no heat recovery chiller with electric room fan coils, the energy cost savings was the exact same. And those were the two strategies that we were really looking at. And in the end, the heat recovery chiller option was a bit more expensive. And so working with the team, we decided to go with a water side economizer on the project, which was really driven by the idea that we couldn't go with active heat recovery due to the district energy connection. So interesting, and I guess something to consider if anybody's building a lab in the Lower Mainland in a district energy area. So moving on to some sustainable design strategies that we have for this building, and really just understanding that I think for a lot of people, there's always a want to have a big catch-all in energy savings, but I just want to try to make it clear that with labs, I think a lot of times we just need to remember that energy efficiency happens when we combine a lot of simple strategies. And so for this building, because of the district energy connection, the heating system was relatively simple, so we went with a higher delta T on the heating system than what we might a lot of times when we're looking at heat recovery chillers providing part of that heat. And so a bigger delta T of 40 degrees Fahrenheit on the heating side of things. VFD obviously on pumps and fans, low velocity air handling systems. So we were actually able to get away with bigger air handlers and lower velocity and bypasses around our coils as well, just to try to reduce as much as we could the pressures through the air handlers. High efficiency open loop cooling towers, water side economizer. And so just combining all of those strategies has really helped our efficiency numbers. The next one that we did that took a little while was recovering exhaust air heat. So the district energy lets us recover heat, but the issue is that they wouldn't let us recover heat through an active means with chilled water. So we've got a runaround loop that we've designed, and it was difficult to look at effective heat recovery that way. And so what we did was take our initial runaround loop that we were provided when we got selections for our heating or for our runaround coils, and we just went through some iterations of it. And we took our efficiency of that loop from about 40% up to 60%. And we did that through increasing our peak max pressure drop on the coils, which typically we'd want to keep it around 10 feet. And looking at increasing that, we were able to get about 20% more efficiency on the system as a whole. And we didn't even have to go that high. We're still less than 17 feet ahead on the runaround coils. And pumps on that runaround coil on VFDs, so that when we don't need the peak heat recovery, then we're operating at lower pump pressures all around the system. So that's where increasing that pressure really didn't affect us too much in terms of the overall energy savings. And we'll show in the next couple slides, but we've got a single coil operation for the lab air handlers. And I know this might not be the best strategy for colder climates. In the lower mainland, we're not as worried about freezing, so we might not have a preheat coil that you might look at for colder climates where you're at -40 or some other temperature like that in Winnipeg or any of the northern climates. And so we were a lot more comfortable knowing that we'd be okay using water in our system and just using the one coil to heat and cool. And so I'll show how we did that as well. And our supply temperature is really going to be maintaining around 55 degrees because of the reduction in airflows that we're going to get into later as well. But that really helps us be able to recover heat throughout most of the heating season. And so this is really what our system looks like. And you can see that from the exhaust to the supply, that is showing the one coil that we've got in the supply air handler. And so that coil is going to be doing heating and cooling whenever it's needed. And on the right-hand side of the page there, you can see over here where we've got switch over from either heating or cooling. And from that, we're going to be feeding to our heat exchanger and topping up the system whenever we can't get enough of either the heating or cooling that we need to that coil. And so we're going to be going through that supply, recovering as much heat as we can through the exhaust, and then topping up any heat that we need through the heat exchanger and then into our supply air handler. And so through this, we were able to really increase the effectiveness of our system and reduce the pressure drops through our supply air handler as well, which has added to the efficiencies that we've gotten in the building. Air transfer, I think this has been talked about a decent amount throughout Canadian projects. And so if you ever get a chance to look at reusing office or administrative air into your lab systems, it's really one of the best ways to recover heat in a laboratory. When we look at air changes in labs, we, I think, sometimes get stuck on the idea that it needs to be 100% outside air, but we all just need to remember that those air changes are really looking for clean air. And ASHRAE 62 is still requiring or identifying how much outside air we need in a lab. And so typically that's going to be a lot lower than the 8, 10, 12 air changes that labs typically are going to be operating at. And so here you can see in the background photo that just like the layout plans that I had, the left-hand side here is typically classroom administrative air, or space rather. Big atrium in the middle. The penthouse is up top above the skylights here on either side, and then the lab air on the other, or the lab air spaces on the other side. And so transferring that air to our lab systems really made a ton of sense for 100% effective heat recovery, basically. And so just a little schematic here to show what it really entailed was, from the left of the page, the clean return air from those office spaces and classroom spaces, returning up into this big atrium, and either mixing back with the air handlers feeding those areas, or feeding back into our lab air handler on the right-hand side of the page. Any overpressurization that we might need or transfer air into those labs was again being used from the clean return air through the atrium and then transferring over into the lab spaces. And so any air that we have that we don't need to exhaust out because it can be used somewhere is going to be used in the building. And so whenever we've got free air left, we're going to return that back to our lab system. And so again, just a really easy way in a lab to get effective heat recovery from air that's otherwise just going to be exhausted out of the building. And so one of the big ones that we looked at was air quality monitoring, and obviously the air acuity system. And the big questions that we looked at were, why should we measure, and why should we try to convince anybody to be using this system in this lab? And one of the biggest ones for us was user safety, and having records and proof of good and bad lab practices, which is one of the big selling points for this system as a whole. And it really gives the occupational health and safety people at the university a lot more information and tools to use to talk to their researchers and make sure that they're actually creating safe environments for themselves and their research students as well. And then obviously from that, energy reduction is another big reason to go this way. And then what can be measured, and looking at that was temperature and humidity. So using our system to kind of double up on it and maintain, or rather measure the temperature and humidity without separate sensors. And so not doubling up on sensors in those labs. CO2 as well, to make sure that we know how much outside air we need to deliver to those spaces. TVOCs and particulates. And if you ever need to, you can measure other particles or specific chemicals, but you just need to be careful in what you're doing, because if you need instantaneous measurement of anything, then you really need to make sure that you're using separate sensors. In this building, we actually have 3 labs that have the possibility to be used for hydrogen research. And so knowing that if something goes wrong in those labs, that needs to be measured right away, and we need alarms to happen right away. And with the air acuity system, it takes measurements in each lab about every 10 to 15 minutes. And so it's just not quick enough to be the source for that alarming. And so we've got separate sensors in those labs that are specifically measuring the levels of hydrogen in those labs. So just be careful when you're looking at different chemicals and what's being used and what you can rely on the system to measure. And so from this, we looked at the operating parameters for the airflow in the labs and came to the following things, which were 4 air changes per hour for normal operation in both our teaching and our research laboratories, and obviously ramping up. And then in the teaching classrooms, unoccupied operation, which was going to be identified through occupancy sensors that are taking off of the lighting sensors, would be just 0 air changes. So we just turn things off when people aren't using the teaching classrooms. And in the research labs, we're going to be ramping down to about 2 air changes to make sure that we keep getting airflow in those labs. And again, occupancy sensors are doubled up on the lighting sensors, just to kind of piggyback on systems that are already there. Additional precaution in each lab is the emergency stop. And so we've made sure that the emergency electrical cutoff that we've got in each lab is connected to our ventilation systems. And if somebody presses that button, it's just going to open up all of our exhaust and our supply air and just ventilate the room as much as it can. And we've got max air changes at about 8 air changes. And so if anybody has had a spill or thinks that they've had a spill and they run out of the lab and they press that button, then it's just going to ramp everything up to 100% airflow, even if the air acuity system hasn't measured that room yet. Everything's going to go into an emergency mode. So I think precautions like that need to be considered as well when we're looking at these systems, again, because they don't react quickly. They take measurements pretty periodically. So we just need to make sure that those safeties are still in place. And what aspects of our lab made the air acuity system make sense And I think everybody needs to make sure that it is right for the project and not just try to shove it into a project because it's the thing that people are using. And so for us, it has limited fume hoods in the building. It's a lot of robotics work and other things that don't necessarily need chemicals. And so we're limited to 2 fume hoods per lab. We've got no clean rooms or animal holding areas, but I know animal holding areas might be a different thing in the coming years with some rewriting of those codes. It's a clean research program. Like I said, a lot of robotics and other types of computer oriented mechanical research. The mechatronics program, supply systems, which is allowing for increased flexibility of the exhaust, and primary exhaust airflow reduction. So we're not a constant volume on the exhaust air, which is allowing us to turn those systems down, which is obviously the primary driver of the air acuity system on the energy side. And so moving from that, just simple equipment efficiencies that we looked at. We've got magnetic bearing chillers, so increasing the efficiencies on our low cooling side of things. The mag bearing chillers really operate more efficiently at lower loading compared to typical chillers. And just to make sure that we were okay on our really low loading before the building's really fully occupied, and in the shoulder seasons, we've got one smaller 60-ton scroll chiller that's going to deal with those really small loads in the building. Electronic filters, and the reason that we looked at this was because our intakes they're about 5 stories up from it, but they're above the generator exhaust. And we wanted to make sure that we didn't have issues with the generator exhaust whenever they are testing it, or should the building go down and researchers think that the building has issues with when they start smelling generator exhaust or diesel fumes in the building. So that was the primary driver of that. The filters with an effective MERV value of 15, and if we lose the electronic piece of it, they're still at a MERV 13 filter. So we just wanted to be cautious on that. And then looking at just an increased overall indoor air quality in the building. So moving on from the design side of things and trying to understand the student learning aspect of the building, because it is sustainable energy and engineering building, the hope was that we could kind of bring some of that to the students. And we still haven't got there. The building is being commissioned right now, and so it'll be interesting to see how effective this is. But the first part of it was, and unfortunately the picture to the right is not this building, but the idea of the mechanical roof spaces being open for students and ready for the researchers in the building. So structurally, it was designed for loading of solar panels or wind turbines, or a few other different research programs that could want to go up onto that roof. So it's ready for somebody to get up there and do some research on different sustainable energy programs. And so that was step number one, and it shockingly took a decent amount of design iteration with the architects, with structural, with us looking at piping in for the possibility of future hydronic solar panels, electrical, making sure that they had provision for photovoltaic arrays, and making sure that the roof was okay to hold a class of 30 kids to go look at what's up there as well. So really opening up those areas for student engagement, because not only is the roof open, our mechanical spaces are open, and they're going to be taking kids through those spaces. They're going to be really designing the spaces once our commissioning is done around the idea of showing kids what is happening in the inside of the building, the pieces that people don't typically see. Interactive displays are going to be allowed for throughout the main entrances of the building and up in the mechanical room as well, where it's going to show how the building is operating, what sort of energy efficiencies we're at, where we're saving energy, and it's going to be, the intent is that students are going to have access to that through the web as well, with just general read-only access to the mechanical BMS. So looking at the different experiments that could be done up on the roof. There, just some pictures of the penthouse and how much space we've actually got up there to allow students to be able to walk through and to be able to take 20 or 30 kids up into that penthouse room and show them around and show them what's going on. And so the main skids for the pumps on the left-hand side that are really going to be driving the hydronic systems, big air handler in the middle of the page with the chiller room just to the middle of that photo, big smoke exhaust and general return air fans that are going to be open and right next to the big air handler. And so it was nice that we were able to get enough room in the penthouse to make that a possibility. And moving out of our construction phase and into when SFU takes over, the intent is going to be coloring the piping, making sure that it's fully interactive that way, and a lot more obvious in terms of what's heating piping, what's cooling piping, domestic water, and those sorts of things. And so really making it interactive that way. Just some examples of what we're going to be hoping to put into the DDC that people are going to be able to see in terms of what sort of energy savings we're getting from the air acuity system. So display use comparisons for energy, system operations, showing them specifically what's happening in the building at that time, and really viewing it from anywhere, from their desktop or on different screens throughout the building. So moving on to the last little bit is the project delivery piece of it, which for me was one of the more interesting pieces, and I think has been a good learning exercise. And so as anybody moves into a new lab, think about how the project is being delivered and maybe whether or not it's the best way to go about it. And each lab is going to be different, each project is going to be different. And so for us, we had a few issues where it really drove what we were doing. So I know a number of the buildings that have recently been finished were SIF funded from the federal government program, which this building was. We had a fixed overall budget, so really set at about $80 million. And so from that, we decided with the construction management team that we would look at doing a design assist for the project for the mechanical tender. And so this is where it was a little bit different in that electrical did not go with the design assist method. They went to straight design bid builds and went to a full electrical tender. And we looked at what we could do to make sure that we brought somebody on board sooner than the completion of our tender documents. And so we brought them on at about 60% completion. We didn't want to bring them on right at the outset of the project because we thought that the design was really needing to look at the entire building. We needed to make sure that we were coordinating with the architect and that we really drove what the mechanical systems wanted to be, so that costs weren't necessarily the first thing that we thought about when we started designing. And so when we were about 60% done our drawings is when we put that out to a design assist tender. And from that, the contractors that were bidding on it had a full understanding for what the mechanical systems were and what the intent of the building was. And so it went out as maximum upset tender to those contractors, where they were going to give their maximum upset number for completion of the mechanical portion of the project, and it would include them being involved in the remaining 40% of the design and making sure that we went through, whether it be cost savings to make sure we could meet their maximum upset pricing, or whether it was that we were collaborating with different ideas, or maybe looking at different system types or equipment types to make sure that we were giving the best value to the owner as well. And so from that, we had at our IFC drawings, our project budget was at about $13.6 million mechanically, which was right at about what the maximum upsets pricing the contractor had provided was. So we really did our best to maintain that pricing that they had provided, and we worked really hard with the mechanical contractor to make sure that we were doing that. The current project mechanical costs after the IFC drawings are at about $13,850, and so we're at about a 2% change order for a really complex lab. And really, apart from obviously what I think were amazing drawings that we provided to the contractor, the contractor had buy-in, and they had the intent of the design was theirs as well. So they couldn't look at the idea of something not necessarily being on the drawings and asking for extras, and so it reduced how much they could ask for. And it also wasn't there wasn't any fighting between us and the contractors when something wasn't necessarily clear on the drawing. We simply talked to them, made sure that everybody was clear on the intent, and as long as we were maintaining the intent, then we could look at maybe a solution that was a little different than maybe what we had thought, but the same intent was there. Or whether it was just something that wasn't necessarily shown, but the contractor understood that it really needed to be there for the system to work. Those things weren't extras to the project. And so that really helped reduce the amount of change orders or extra costs mechanically for what really is a really complex lab. And as much as we try to coordinate everything with the other disciplines, there's always going to be things that do come up. It's construction, and so this really helps reduce that. So ownership of the mechanical contractor on the design was a big one. That helped reduce RFIs and change orders. RFIs was a big one. I mean, we had the relationship with the contractor to where they would call us before necessarily putting things in paper. So things that were really simple questions of, is this what you're intending? Yeah, that's what we're looking at. Didn't need paperwork or paper trails to be produced, whereas a typical tender might see a lot more paperwork just in contractors maybe trying to set themselves up should there be delays or anything like that. And we didn't really have that at all on this project. The coordination of drawings, from our side, we did do our best to try to coordinate as much as we could, but since the contractor was involved throughout the last 40% of design, they also looked at their 3D BIM modeling of the really complex areas. So they modeled the penthouses before we were even done our design to make sure that everything fit, to make sure that everything was coordinated with structure, with architecture, and they came up with a lot of things that were clashing that maybe we wouldn't necessarily have noticed structurally up in the penthouse and that. So that coordination was helped by the contractor being on board and doing a lot of their pre-work that wouldn't necessarily have been done prior to design being finished on a typical building. And like I said, communication with the mechanical contractor was a big one, and I think can really help anybody on a project like this. And so I know I'm a little bit early, but that is all that I've got. My contact info is there for anybody that might want to get in touch and chat about this project or anything else that's out there.
Great. Thanks very much, Kevin. That was a very interesting building. It looks like you had a few challenges there for sure.
Yeah.
We do have a question for you. In the case of a reduced airflow situation due to unoccupied system operation, how do you deal with the potential of chemical buildup due to improper bench practice or chemicals left at the bench or improperly stored in the laboratory?
So that's where the air acuity system really comes into play. It's going to continuously be monitoring those labs. And so those lower set points really just are the lower set points. But as air acuity starts to sense anything in the labs building up, it's going to start increasing those airflows up to 8 air changes an hour. And so if we had anything where it was a full spill and those 8 air changes weren't fully clearing out the room, then alarms would go as well, so that the maintenance team would understand what was going on or that there was an issue in a lab. So those are just the lower limits, but ultimately, if the labs do see bad practice from the researchers or from students, then the airflows are going to maintain high, which is why the occupational health and safety, this really gives them fuel to take to researchers to show them that even though their lab might look clean, they've got clear evidence that they're not maintaining good practice in their research. So I think those things combined really help, I guess, convince owners that that's a system that they can use in more than just an energy-saving way. Great.
I'll just give, there are no other questions right now. I'll just give everybody a minute or two just in case there's any last-minute things here. One of the things that caught my attention was because of your unique climate that you have in Vancouver, are you having any issues with this deep freeze that you're going through?
No, it's still, I mean, it's a deep freeze, but it's still only, I think it's only gotten to -6 or 7, and our design temp is still -9 about here. So it's been snowy, but it hasn't been super, super cold yet. So no.
Well, you're almost through it. If I recall, springtime in Vancouver is like mid-February, so.
The flowers were blooming before we had this cold snap. So.
That's crazy. That's crazy. Okay, well, there's nothing else that's come through, Kevin, so I guess we'll let you go. I just, on behalf of SLCan, would like to say thank you very much for your presentation.
Thanks a lot, and thanks to everybody that was listening. And like I said, if anybody does have any other questions that pop up, let me know. There was obviously a lot to go through, and I went through it a little bit quickly. So if you have any other questions or thoughts, don't hesitate to give me a shout or send me an email.
Great. All right. Thanks very much, Kevin.
Thanks a lot.
Okay, bye for now.